IC bonding, wire bonding, thermosnic bonding, flip chip or tape automated bonding, tab. IC encapsulation or integrated heat spreader, IHS, installation molding, using special plastic molding compound that may contain glass powder as filler to control thermal expansion. Baking. Electroplating, plates the copper leads of the lead frames with tin to make solder angesia. Laser marking or silk screen printing. Trim and form, separates the lead frames from each other, and bends the lead frame pins so that they can be mounted on a printed circuit board. IC testing. Additionally, steps such as right edge may be carried out. Progress of miniaturization, and comparison of sizes of semiconductor manufacturing process nodes with some microscopic objects and visible light wavelengths. Prevention of contamination and defects. When feature widths were far greater than about 10 micrometers, semiconductor purity was not as big of an issue as it is today in device manufacturing. As devices become more integrated, clean rooms must become even cleaner. Today, fabrication plants are pressurized with filtered air to remove even the smallest particles which could come to rest on the wafers and contribute to defects. The ceilings of semiconductor clean rooms have fan filter units, FFUs, at regular intervals to constantly replace and filter the air in the clean room. Semiconductor capital equipment may also have their own FFUs. The FFUs, combined with raised floors with grills, help ensure laminar airflow, to ensure that particles are immediately brought down to the floor and do not stay suspended in the air due to turbulence. The workers in a semiconductor fabrication facility are required to wear clean room suits to protect devices from human contamination, to prevent oxidation and to increase yield. FOUPs and semiconductor capital equipment may have a hermetically sealed pure nitrogen environment with ISO Class 1 level of dust. FOUPs and SMIF pods isolate the wafers from the air in the clean room, increasing yield because they reduce the number of defects caused by dust particles. Also, fabs shave as few people as possible in the clean room to make maintaining the clean room environment easier, since people, even when wearing clean room suits, shed large amounts of particles, especially when walking. 35, 36, 37 wafers. A typical wafer is made out of extremely pure silicon that is grown into monocrystalline cylindrical ingots, up to 300 millimeters, slightly less than 12 inches, in diameter using the Czochralski process. These ingots are then sliced into wafers about 0.75 millimeters thick and polished to obtain a very regular and flat surface. Processing. In semiconductor device fabrication, the various processing steps fall into 4 general categories: deposition, removal, patterning, and modification of electrical properties. Deposition is any process that grows, coats, or otherwise transfers a material onto the wafer. Available technologies include physical vapor deposition, PVD, chemical vapor deposition, CVD, electrochemical deposition, ECD, molecular beam epitaxy, MBE, and more recently, atomic layer deposition, ALD, among others. Deposition can be understood to include oxide layer formation by thermal oxidation or, more specifically, locus. Removal is any process that removes material from the wafer. Examples include etch processes, either wet or dry, and chemical mechanical planarization, CMP. Patterning is the shaping or altering of deposited materials, and is generally referred to as lithography. For example, in conventional lithography, the wafer is coated with a chemical called a photoresist. Then, a machine called an aligner or stepper focuses a mask image on the wafer using short wavelength light. The exposed regions, for positive resist, are washed away by a developer solution. After removal or other processing, the remaining photoresistors removed by dry plasma ashing or wet chemistry. 38. Modification of electrical properties has historically entailed doping transistor sources and drains and polysilicon, originally by diffusion furnaces and later by ion implantation. These doping processes are followed by furnace annealing or, in advanced devices, by rapid thermal annealing, RTA, to activate the dopants. Modification of electrical properties also extends to the reduction of a material's dielectric constant in low insulators via exposure to ultraviolet light in UV processing, UVP. Modification is frequently achieved by oxidation, which can be carried out to create semiconductor insulator junctions, such as in local oxidation of silicon, locus, to fabricate metal oxide field effect transistors. Modern chips have up to 11 or more metal levels produced in over 300 or more sequence seed processing steps. Front end of line, field processing. Field processing refers to the formation of the transistors directly in the silicon. The raw wafer is engineered by the growth of an ultra-pure, virtually defect-free silicon layer through epitaxy. In the most advanced logic devices, prior to the silicon epitaxy step, tricks are performed to improve the performance of transistors to be built. One method involves introducing a straining step wherein a silicon variant such as silicon germanium, SiGe, is deposited. Once the epitaxial silicon is deposited, the crystal lattice becomes stretched somewhat, resulting in improved electronic mobility. Another method, called silicon on insulator technology, involves the insertion of an insulating layer between the raw silicon wafer and the thin layer of subsequent silicon epitaxy. This method results in the creation of transistors with reduced parasitic effects. Gate oxide and implants. Front-end surface engineering is followed by growth of the gate dielectric, traditionally silicon dioxide, patterning of the gate, patterning of the source and drain regions, and subsequent implantation or diffusion of dopants to obtain the desired complementary electrical properties. In dynamic random access memory, DRAM, devices, storage capacitors are also fabricated at this time, typically stacked above the access transistor. The now defunct DRAM manufacturer Chimunda implemented these capacitors with trenches etched deep into the silicon surface. Back end of line, bill, processing. Metal layers. Once the various semiconductor devices have been created, they must be interconnected to form the desired electrical circuits. This occurs in a series of wafer processing steps collectively referred to as bill, not to be confused with back end of chip fabrication, which refers to the packaging and testing stages. BEO processing involves creating metal interconnecting wires that are isolated by dielectric layers. The insulating material has traditionally been a form of SiO2 or a silicate glass, but recently new low dielectric constant materials are being used, such as silicon oxycarbide, typically providing dielectric constants around 2.7. compared to 3.82 for SiO2, although materials with constants as low as 2.2 are being offered to chip makers. High dielectrics may be used instead. Interconnect. Synthetic detail of a standard cell through 4 layers of planarized copper interconnect, down to the polysilicon, pink, wells, grayish, and substrate, green. Historically, the metal wires have been composed of aluminum. In this approach to layering, often called subtractive aluminum, blanket films of aluminum are deposited first patterned, and then etched, leaving isolated wires. Dielectric material is then deposited over the exposed wires. The various metal layers are interconnected by etching holes, called vias, in the insulating material and then depositing tungsten in them with a CVD technique using tungsten hexafluoride. This approach can still, and often is, used in the fabrication of many memory chips such as dynamic random access memory, DRAM. Because the number of interconnect levels can be small, no more than 4. More recently, as the number of interconnect levels for logic has substantially increased due to the large number of transistors that are now interconnected in a modern microprocessor, the timing delay in the wiring has become so significant as to prompt a change in wiring material, from aluminum to copper interconnect layer, and a change in dielectric material, from silicon dioxides to newer low insulators. This performance enhancement also comes at a reduced cost via damascene processing, which eliminates processing steps. As the number of interconnect levels increases, planarization of the previous layers is required to ensure a flat surface prior to subsequent lithography. Without it, the levels would become increasingly crooked, extending outside the depth of focus of available lithography, and thus interfering with the ability to pattern. CMP, chemical mechanical planarization, is the primary processing method to achieve such planarization, although dry etch-back is still sometimes employed when the number of interconnect levels is no more than 3. Copper interconnects use an electrically conductive barrier layer to prevent the copper from diffusing into poisoning its surroundings. Wafer test. The highly serialized nature of wafer processing has increased the demand for metrology in between the various processing steps. For example, thin film metrology based on ellipsometry or reflectometry is used to tightly control the thickness of gate oxide, as well as the thickness, refractive index, and extinction coefficient of photoresist and other coatings. 39. Wafer test metrology equipment is used to verify that wafers haven't been damaged by previous processing steps up until testing. If too many dies on one wafer have failed, the entire wafer is scrapped to avoid the costs of further processing. Virtual metrology has been used to predict wafer properties based on statistical methods without performing the physical measurement itself. 1. Device test. Once the front-end process has been completed, the semiconductor devices or chips are subjected to a variety of electrical tests to determine if they function properly. The percent of devices on the wafer found to perform properly is referred to as the yield. Manufacturers are typically secretive about their yields, 40, but it can be as low as 30%, meaning that only 30% of the chips on the wafer work as intended. Process variation is one among many reasons for low yield. Testing is carried out to prevent faulty chips from being assembled into relatively expensive packages. The yield is often but not necessarily related to device, die or chip size. As an example, in December 2019 TSMC announced an average yield of 80%, with a peak yield per wafer of and GT 90% for their 5nm test chips with a die size of 17.92 mm. The yield went down to 32.0% with an increase in die size to 100 mm. 41. The number of killer defects on a wafer, regardless of die size, can be noted as the defect density, or D0, of wafer per unit area, usually centimeter 2. The fab tests the chips on the wafer with an electronic tester that presses tiny probes against the chip. The machine marks each bad chip with a drop of dye. Currently, electronic dye marking is possible if wafer test data, results, are logged into a central computer database and chips are binned, i.e. sorted into virtual bins, according to predetermined test limits such as maximum operating frequencies, /clocks, number of working, fully functional, cores per chip, etc. The resulting binning data can be graphed, or logged, on a wafer map to trace manufacturing defects and mark bad chips. This map can also be used during wafer assembly and packaging. Binning allows chips that would otherwise be rejected to be reused in lower-tier products. as is the case with GPUs and CPUs, increasing device yield, especially since very few chips are fully functional, have all cores functioning correctly. For example, fuses may be used to disconnect parts of chips such as cores, either because they didn't work as intended during binning, or as part of market segmentation, using the same chip for low, mid and high-end tiers. Chips may have spare parts to allow the chip to fully pass testing even if it has several non-working parts. Chips are also tested again after packaging, as the bond wires may be missing, or analog performance may be altered by the package. This is referred to as the final test. Chips may also be imaged using X-rays. Usually, the fab charges for testing time, with prices in the order of cents per second. Testing times vary from a few milliseconds to a couple of seconds, and the test software is optimized for reduced testing time. Multiple chip, multi-site testing is also possible because many testers have the resources to perform most or all of the tests in parallel and on several chips at once. Chips are often designed with testability features such as scan chains or a built-in self-test to speed testing and reduce testing costs. In certain designs that use specialized analog fab processes, wafers are also laser trimmed during testing, in order to achieve tightly distributed resistance values as specified by their design. Good designs try to test and statistically manage corners, extremes of silicon behavior caused by a high operating temperature combined with the extremes of fab processing steps. Most designs cope with at least 64 corners. Device yield. Device yield or die yield is the number of working chips or dies on a wafer, given in percentage since the number of chips on a wafer, die per wafer, DPW, can vary depending on the chip's size and the wafer's diameter. Yield degradation is a reduction in yield, which historically was mainly caused by dust particles. However, since the 1990s, yield degradation is mainly caused by process variation, the process itself and both tools used in chip manufacturing, although dust still remains a problem in many older fabs. Dust particles have an increasing effect on yield as feature sizes are shrunk with newer processes. Automation and the use of mini environments inside of production equipment, FOUPs and SMIFs have enabled a reduction in defects caused by dust particles. Device yield must be kept high to reduce the selling price of working chips, since working chips have to pay for those chips that failed, and to reduce the cost of wafer processing. Yield can also be affected by the design and operation of the fab. Tight control over contaminants and the production process are necessary to increase yield. Contaminants may be chemical contaminants or be dust particles. Killer defects are those caused by dust particles that cause complete failure of the device, such as a transistor. There are also harmless defects. A particle needs to be 1/5 the size of a feature to cause a killer defect. So if a feature is 100 nm across, a particle only needs to be 20 nm across to cause a killer defect. Electrostatic electricity can also affect yield adversely. Chemical contaminants or impurities include heavy metals such as iron, copper, nickel, zinc, chromium, gold, mercury and silver, alkali metals such as sodium, potassium and lithium, and elements such as aluminum, magnesium, calcium, chlorine, sulfur, carbon, and fluorine. It is important for these elements to not remain in contact with the silicon, as they could reduce yield. Chemical mixtures may be used to remove these elements from the silicon. Different mixtures are effective against different elements. Several models are used to estimate yield. They are Murphy's model, Poisson's model, the binomial model, Moore's model and Seed's model. There is no universal model. A model has to be chosen based on actual yield distribution, the location of defective chips, for example, Murphy's model assumes that yield loss occurs more at the edges of the wafer. Non-working chips are concentrated on the edges of the wafer. Poisson's model assumes that defective dies are spread relatively evenly across the wafer, and Seeds's model assumes that defective dies are clustered together. 42. Smaller die